language AI models we're all using actually work, how they think.
It's fascinating, isn't it? And right now, a lot of their power comes from something called test time compute.
Right, test time compute. So basically, they just throw a ton of processing power at the problem the moment you ask a question.
Exactly. You ask, they compute. Hard. It's the standard way, and often the more compute you use then, the better the answer you get.
Makes sense.
But, well, you can imagine relying only on that real-time, super intense processing. It can start to hit limits, right? Speed limits and definitely cost limits.
Yeah, I could see that, especially if you're going back and forth like in a chat or working with the same document or something.
Precisely. Those stateful applications where context matters across interactions, that's where it gets tricky.
Okay, so that brings us to this deep dive. We're looking at a pretty clever alternative idea. It's called sleep time compute.
Sleep time compute. It sounds relaxing, but it's actually quite active.
Huh. Yeah, not quite napping AI. So the core idea is, what if the model could do some heavy lifting, some thinking, before you even ask your question?
Exactly. Instead of just waiting passively, it uses that downtime, the sleep time, to anticipate,
Right.
to look at the information it has and pre-process it.
Almost like digesting the information.
Yeah.
Getting insights ready in the background.
You got it. It's like it's reviewing the notes before the meeting even starts.
Yeah.
It analyzes the context, makes connections, prepares the ground.
Okay, so that's our mission for this deep dive, then.
Yeah.
Really getting into this sleep time idea. How does it actually, function?
Uh-huh.
And what are the potential upsides for you listening? Are we talking faster answers, maybe lower costs behind the scenes? Or does it enable different kinds of interactions?
Good questions. And we're basing this exploration on some really interesting research, specifically a paper titled Sleep Time Compute, Beyond Inference Scaling at Test Time.
Lineal, right.
That's the one. And they really zero in on that problem we mentioned. Scaling test time compute just keeps getting more demanding.
Especially for those stateful apps, right?
Yeah.
Document Q&A, coding agents, chat bots.
Exactly. The paper points out that high latency, high cost. It's a real bottleneck if the AI has to constantly reevaluate everything from scratch with every single query.
Like rereading the entire chat history every time I ask a follow-up? That sounds incredibly inefficient.
It is. And sleep time compute basically offers a potential path around that.
Okay, so it's not literally sleeping and dreaming.
Yeah.
How does this offline thinking actually happen? What's going on, under the hood?
Well, the researchers describe this process where during the offline phase, when it's not busy answering you, the model is prompted to really engage with the context it has.
The context being, say, a document I uploaded.
Yeah.
Or the code files for a project.
Precisely. And it uses its capabilities, its language understanding, to identify key themes, make inferences, draw conclusions, basically creating a richer, more processed version of that raw information.
Ah, okay. So it's not just storing the raw text. It's building its own internal summary or a knowledge map, highlighting what it thinks might be relevant later on.
That's a great way to put it, like pre-annotating the important bits. It's generating this pre-digested knowledge base.
Right, like getting meeting minutes before the meeting starts, with the key points already pulled out.
Spot on analogy. So then when you, the user, finally ask your question, this pre-processed information, this richer context, is fed into the model alongside your actual query.
And because a chunk of the sort of initial understanding is already done.
Exactly. Because that heavy lifting happened during sleep time, it can often generate the answer much faster and, crucially, using less of that expensive on-demand test time compute.
Okay, that makes intuitive sense. Now, I know the researchers tested this. They used some math reasoning problems, didn't they?
Yeah.
But modified somehow.
They did. They used data sets like GSM-Symbolic and anew, but adapted them to be stateful, meaning there was context carrying over between problems, simulating that ongoing interaction.
And what did they find? Did the sleep time approach actually, help?
Oh, absolutely. The results were pretty striking, actually. They found that by using sleep time compute, they could drastically cut down the amount of test time processing needed.
How drastically?
In some cases, to reach the same level of accuracy, they needed up to 5 times less test time compute.
5 times? Wow. That's a massive reduction in the compute needed right at that moment. Huge implications for speed, for cost.
Definitely. But it wasn't just about using less test time compute. They also looked at what happens if you invest more in the sleep time phase.
Meaning, let the model think even more deeply offline.
Exactly. Give it more computational budget during that pre-processing stage. And what they saw was really interesting.
What happened?
Accuracy went up, significantly. On one math dataset, they saw accuracy gains of up to 13%, and on another, it was up to 18%.
18% improvement just by letting it think more beforehand.
It strongly suggests that doing that upfront, offline work, that sleep, translates into better quality answers later on. For you, learning something new, it's like more study time leads to better recall on the test, right?
Yeah, that tracks. Okay, so better efficiency, potentially better accuracy. Now, paper mentions amortization, so that's a bit financial. How does that fit in?
It's a really practical point about cost effectiveness. Think about using an AI to help you understand a long research paper.
Okay.
You probably won't ask just one question, right? You'll likely ask several follow-ups, digging deeper.
Yeah, definitely.
So if the model has done its sleep time compute on that paper once, the insights it generated, that pre-processed knowledge, can be reused for all your subsequent questions about it.
Ah, I see. So the initial cost of that sleep thinking gets spread out over multiple queries.
Precisely. You amortize the cost. And this makes the average cost per query much lower. The researchers found they could drop that average cost by up to 2.5 times in one of their multi-query setups.
So if you're likely to interact with the same context, repeatedly exploring a topic, analyzing a document, working on a project, sleep time compute could be seriously more resource efficient.
That's the idea. And it leads into another really fascinating finding they had about when sleep time compute actually shines the brightest.
Okay.
They found a strong link between how predictable your question is, given the context, and how much benefit you get from sleep time compute.
Predictable. That sounds subjective. How on earth do you measure the predictability of a question?
Yeah, it's not simple guesswork. They used a pretty clever technique involving something called log probability, calculated by another powerful language model, Llama 270B in this case.
Log probability. Okay, break that down a bit.
Think of it like this. Based on the current conversation or document context, how likely does a big language model think this specific question is to come next? A higher log probability means the question is more expected, predictable.
Okay, so it's a statistical measure of how much a question flows naturally from the context. Got it. So what was the connection they found?
What's really cool is that the gap in accuracy, the difference between using sleep time compute versus just standard test time compute, got much wider for those more predictable questions.
Wider. Meaning sleep time helped more when the question was expected.
Exactly. If the model could sort of anticipate the likely direction of your questions during its sleep phase based on the context, it was way better prepared. It could leverage that pre-computation much more effectively to give an accurate answer using less test time effort.
That's a real insight, isn't it? It implies that how we interact matters. If our questions follow logically from the context we provide, this sleep time approach can prepare better.
Makes perfect sense. Conversely, if you ask something totally out of left field, completely unrelated to the context, well, the pre-computation might not help as much for that specific query.
Right, because it couldn't have reasonably anticipated it. Okay, so predictability is a key factor.
Yeah.
Do they look at this in like a more real-world task beyond math problems?
They did. They ran a case study on agentic software engineering tasks, basically using an AI agent to help modify code based on a feature request.
Okay, like add a dark mode toggle to this app, something like that.
Yeah, tasks like that, which involve understanding existing code and figuring out what needs to change. It's complex, multi-step work.
And how did sleep time compute fare there in that practical setting?
What they noticed was interesting. When they deliberately limited the amount of test time compute available, simulating perhaps a resource constraint or a need for faster interaction.
Okay.
Using sleep time compute led to better performance. Specifically, the AI agent was better at identifying the correct files in the code base that needed modification to implement the feature.
So it helps focus the effort more effectively when time or resources were tight.
Seems like it. They measured up to a 1.5x reduction in the test time tokens needed, essentially, the amount of real-time processing to achieve similar F1 scores, which is a measure of accuracy in this kind of task.
So even in complex practical things like coding assistance, doing some homework on the code base beforehand, the sleep time compute can make the AI more efficient when it actually has to act.
Exactly. It suggests this isn't just a theoretical benefit for abstract problems, it has legs in practical applications too. For you, using, say, an AI coding assistant, this could mean faster, more targeted help.
Okay, so let's try and wrap this up for you, the listener. The big picture here seems to be that sleep time compute isn't really about replacing the standard test time approach entirely.
No, not at all. It's more like a powerful complementary strategy, a different tool in the toolkit.
Right, and the potential benefits seem pretty compelling. That possibility of drastically cutting down test time compute.
Yeah, that five-fold reduction they saw in some experiments is eye-catching.
And potentially improving accuracy at the same time, just by investing more in that offline thinking.
Absolutely. Plus, the cost-saving angle, spreading that initial compute cost over multiple related questions through amortization, that paints a really interesting picture for many applications you might interact with.
And that predictability insight feels key too. The better the model can anticipate your likely questions from the context.
The more mileage it gets out of that sleep time preparation, it really highlights the interplay between context and interaction design.
Yeah. And the software engineering example shows it's not just theory. It can provide real benefits in complex tasks, especially maybe when you can't just throw infinite compute at the problem in real time.
Precisely. It offers a way to be smarter with the resources you have.
So here's maybe a final thought for you listening.
Hmm.
How could this idea, this concept of pre-computation or offline thinking, apply maybe to your own work or your own learning?
Interesting question.
Could you, get more efficient or gain deeper understanding by consciously anticipating the questions you might have about a new subject, or by pre-processing information before you really need to dive deep?
It's fascinating, isn't it? Thinking about how these AI strategies might mirror or even inform our own cognitive processes for learning and problem solving more effectively.
Definitely something to mull over.
And hey, for anyone who really wants to get into the nitty-gritty, the researchers have made their code and data available.
Oh, right? They put it on GitHub?
Yep. So if you want to explore the technical details behind the log probabilities or the specific task setups, it's all out there. A great resource for a really deep dive into this specific approach.